Alright, so let's look at 64-bit ARM exploits. And the first thing I'm going to do is stop my 32-bit emulator. So in the Raspberry Pi I do sudo power off. I don't want to run them both at the same time, although you might be able to. And my console on the Raspberry Pi here shows it shutting down. Alright, and so it's sudo start. Alright, so now to start the 64 one, it's sudo start ARM or /start. ARM64.sh. Alright. And the password p@ssw0rd. Alright, that should start the 64-bit emulator. There we go. Alpine Linux booting up. Then we're going to have to fix the networking. It'll take some time to load. I'll clear these other windows. We're going to need more windows into our Ubuntu machine. So I'll leave them connected. These are other SSH windows in. But we won't need it until we get the 64-bit emulator up and the networking fixed. And there's some stuff to install there, which I've already done. Seems like I could make a cron tab that fires like 1 minute after boot up or something to automatically fix the networking. I think I tried that and I couldn't get it working. Anyway, this works. It's just a little bit silly, clumsy process. There it goes, getting upset about clock skew again. come the interfaces. All right. Students and capital P at SSW0RD. All right. So the first two commands just show the problem. The third one is the one that fixes it, where you delete the default. Gateway. That'll have to wait. All right. All right, and that should have fixed it, and I should be able to see that it fixed by running the ping. Good. All right. So the networking is fixed. Now we'll find the Alpine machine's IP address, which is the ETH1 adapter is the local host one, and that's the one we want to SSH to. Yep. So I'll copy that and get one of my Ubuntu machines here. All right, and SSH a student at that address, and it's P at SSW0RD. All right, so here's my console in the Alpine machine, which I don't want to use much, and here's my SSH into the Alpine machine that will work better. All right, and now there's things to install. It is not apt install on Alpine, it's apk add, but it amounts to the same thing. So you can install the GNU debugger, the necessary compiling tools, and Python, and I've already done that. All right, and so if you do uname -a, this is ARM64, 64-bit ARM. So we're going to put the same vulnerable program on here. If I cat pwd.c, this is the same thing that takes hexadecimal input and copies it into a password field that only has room for 10 characters. So it has the same buffer overflow vulnerability, and you can compile it, and it's going to be compiled for 64-bit ARM. You can tell with the file command, pwd will show that this is a 64-bit executable. So we have the same problem with address space layout randomization. If you run it and give it an AA for a password, this password is at this address, and if you run it again and give it AA, it is 4E0, 6E0. Again, it changes every time, and we don't want that, so we have to turn off the randomize VA space again. So that's sudo su minus password. All right, then that command, then exit, and now it should no longer be randomizing. There, I do it 3 times, and it's always F's followed by C20. So now things are not randomly running around, so now we can fuzz it again and show that it crashes. If I put in a long password, a longer one than last time, because we have 64-bit addresses now, and for another reason we're about to see, it does have a segmentation fault when you put in a long enough password. So let's find out why. Because there is a defense in 64-bit ARM that's supposed to protect you from this kind of vulnerability, and we're going to see why it does not work. So you run it here, you feed in that long password, and now it crashes, and you can see down here it's 24, 28, and so on, and if the colors are hard to see, you can do $PC to get it here. 24, 28, 28, 28, 2C. So it is getting some of these characters in the instruction pointer, the program counter. So, to see why, let's disassemble main. And you'll see here's the command that calls the subroutine. Here is the next address. So the next address is a bunch of A's followed by 0C40. That should be the return pointer. And it's highlighted here so you can see it. So we're going to examine the stack. If I list the source code from 39 to 52, and then I see 46 is the line that returns from the subroutine, so I break there and run. Yes, and now I put in a short password of 10, 10, 10, 10. Now I can examine the stack. Need a space here. All right. And so here, here's the 10, 10, 10, 10 I put in, and this is the return pointer before it. This is the defense to prevent buffer overflow attacks. The return pointer comes before the string. So if I make this string longer and longer, I'll never hit that return pointer. So why did it work? It worked because down here, this is another return pointer. This return pointer here is the return from the test PW routine, but this pointer down here is the return pointer when the program exits entirely, returning back to the operating system. So even though I can't overflow and hit the return pointer from this module, I can overflow and hit the return pointer from a different module, which gives me essentially the same ability to control the box. So the defense failed in that regard. And so a long enough password will override it, and therefore it's the same thing again. You make a exploit with dummy shellcode. Now the NOPs are here, and the invalid commands that cause it to return to the debugger is there. And so this is the file called x1. Let me quit out of here and look at it. ex1.py builds the dummy exploit with enough prefix to hit the program counter. This is the value I'm putting in the program counter: A0, A0, B0, B0, C0, C0, D0, D0. There's just a dummy to indicate that I've correctly controlled it. Then I have a NOP sled and a buffer, and I build the attack that way. So if you load this one in the debugger, I've put the output of this in ATT1 and go to GDB minus QPWD and run with ATT1, and it does stop with the address A0, A0, B0, B0, C0, C0, D0, D0. So that means it works. Now I want to examine the stack, and we can just do that from here. At the point of the crash, we'll do 80x the stack pointer, because here you see the 5032 stuff is the NOPs, and here are the invalid commands that will cause it to break. So all I have to do is pick an address somewhere up in the middle of these NOPs. And this one I chose was all F's followed by C60. That'll do. That's an address to jump to. It should run, and it should break when it hits the first one of these, which is going to be CC8. So we can run that code. Let me get out of here. Now I know the address to put in, so that's ex2.py. Now I have the right address to put in here, and I still have a dummy, a NOP sled and dummy buffer, so I can run this with GDB. All right, and run getting data from ATT2, and see it makes it to the illegal instruction here at CC8 where I said it would. So it did jump into the NOPs, and it went NOP, 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 and hit the first one of these invalid commands down here somewhere, around here, and that was this address. So I'm able to execute the NOPs, I'm able to control the program counter. Now all I need is real malware, and once again, on your Ubuntu machine, you can use MSF Venom, and there are some 64-bit exploits. There is not a shell bind to TCP, but there's a reverse shell. And in the reverse shell, it needs to know the address of the command and control server to call back to. So you have to get the IP address of your Ubuntu machine and build it into your exploit. So one of the addresses is 192.168.61, and it should be the same on your system because I made it a manual address. So you make your malware this way with that address built in, which is a property of most malware, most bots these days. You can look in the code of the bot that infects your machine, and you will find the address of the command and control server. This is how researchers often take over botnets. So that makes Python code that does that, and you can put it in the finished exploit here, and I've done all that. So I cat ex3.py, and so here it is, the same address here, which will hit the NOP sled, the same NOP sled. This is the code that came from Metasploit that's going to phone home, and you just print that. So in order to run it, I have to have a listener ready on my Ubuntu machine, which is going to act as the command and control server. So I have to go here. Somehow the window is not letting me come up. Thought I had the other window up there, but I guess I was just an image. All right. All right, this will do. I've got another Ubuntu window. All right, so I have to run MSF console, and I'll use -Q to avoid having a big banner on the top. And here I tell it what to expect. This is the multi-handler. Using this payload, I'm going to get, this is going to run on my target. It's going to phone home. Okay, so I paste in that stuff and then just run. Now it is listening to be called up by the malware. And there I just need to run the attack here, which is pwd getting data from ATT3. And see, it doesn't crash. It says all done. And now it's going to phone home up here. There it comes. Now I have a command shell open. So this is Ubuntu. But if I do who am I, I'm student. And if I do uname -a, I'm on the ARM64 Linux. So I'm on the 64-bit Linux here, remote controlling it, as before, with this reverse shell. All right, and that's it. I made some notes here about how I found some commands to use for break and NOP in 64-bit ARM, but that's it. That's the ARM version of the same thing. So I'm going to exit here, and then that gets me back to there, and I'll stop this video.